Maybe sharing. Oh yeah, we're gonna have show and tell.
Oh, it's show and tell.
Yeah, so you have to tell us what you brought in and why you brought it in and that kind of stuff. It'll be fun. Okay, so continuing with differential equations. We talked already about separable differential equations. Why are they called separable differential equations? If you can talk. Come on, this was important. Why are they called separable differential equations?
Because you can separate.
You have to, not only can you have to separate them. Very good. That's why you're in an AP class. You have to separate the differentials. If you don't, you're going to lose all the points. So get in the habit of doing that. And today we're going to talk about laws of growth and decay. So we do some word problems involving this stuff. I'm pretty sure you did this last year in pre-calc, yes?
Sure.
Yes, you did. It doesn't matter what I say, Rosie. You're going to... Like if I say, like last year in pre-calc, you were breathing, right?
No.
Right, Rosie, no. I held my breath the whole year. Would that be considered bullying? All right, good. Got that out of the way. We're going to talk about the PERT equation. So last year you used the PERT equation. It was introduced to you and you just plugged and chugged. We're going to take a calculus approach to the PERT equation. Not everything is going to be a calculus approach. We will get some stuff where you just plug and chug into the PERT equation. We are going to, as I just said, use calculus to derive that PERT equation. So last year in pre-calc, somebody just said, oh, look at this pretty formula, plug in, use the formula, everybody's happy. In calc, we're not going to be happy with that. We're going to have to derive that. And then, of course, be nice to everyone today.
Yeah, nice to everyone.
No, this is for you, not for me. You should be able to, not me. Okay. So, the PERT equation. It's called the PERT equation, but actually E is raised to the RT. Sometimes it's the KT power. There's a couple other versions of it. So here it is in its true form. P naught is your starting amount. R is your growth or decay rate. Tell me about the growth or decay rate. What does that mean? And don't tell me it's how much it grows and decays. You were thinking that, weren't you, Matt?
A little bit.
Yeah. What do you know about the growth or decay rate? Mm-mm. Good guess. When in doubt, slope.
Yep.
Yeah. Go ahead.
Is it constant?
It is for the situation. Good. Anything else? How do you distinguish between a growth or a decay?
Positive or negative.
Positive or negative. So if it's positive, is it a growth or a decay?
Growth.
It's a growth. And if it's negative, it's a decay. And then, of course, T is time. So something like the spread of zombies would be a positive growth. Okay. One zombie bites one person, or bites two people. Those two people bite two people. Those two people bite two people. Next thing you know, you have a hit show on AMC, right? Okay, so that's an exponential growth. A decay would be something like radiation, and we've got a couple examples in there. Excuse me. In calculus, we see a couple different forms of that same equation. Okay, change the P to a C, change the R to a K. That's not much different. But then we'll also see that little guy, which is going to pop up a little bit. What's the left side of that equation mean?
Derivative of y over time.
But let's change the word derivative, because we're going to be dealing with real world problems. What's another word for derivative? What are the three things for that dy dt? It's a derivative, it's slope of the tangent line, and
Rate of change.
rate of change. We're going to use the rate of change thing. Okay, so this is the rate of change of y with respect to time. So we're going back to problems involving time. And again, c is a constant and y is whatever it is we're talking about. Okay, we good? Let's look at the first one. We got some bacteria. Excuse me. Love for this cough to go away. The number of bacteria in culture increases from 600 to 1,800 in 2 hours, assuming that the rate of increase is directly proportional to the number of bacteria present. Find blah, blah, blah. So last year, you'd see this problem. In fact, you probably did a problem very similar to it. And you would plug in the information that you know, calculate a couple different things, and move on. In calculus, we're going to start from scratch. Okay. So let's do that. Assume that the rate of increase. So how would I express the rate of increase of, well, first of all, let's define some variables. What variables would you like to use?
T.
T for time. And we need another variable. N for, you want to use N for number of bacteria?
No, B for bacteria.
I'm not asking you. Would you like to use N for number?
That's fine.
What's fine?
B's
N,
fine.
you're going to let her bully you into going with B.
You should do N anyway.
I'm going to do N. Hashtag bacteria. It's not really hashtag, that's number. It's silly. That's from the Twitter, in case you don't know. Okay, so the original equation says, assuming that the rate of increase is directly proportional to the number of bacteria present. So how do I express the rate of increase of the bacteria? With respect to time.
1800 minus 6.
No numbers yet.
Number of bacteria over time. Change in number of bacteria over time.
Again, how do you express that in calculus?
DNET.
Thank you. Who said that? Well done.
Thank you.
Is directly proportional to, what does that mean?
Equals.
Equals.
Doesn't that mean it's just that and not that under 1?
No, that's good. That's inversely proportional, which we'll get to later.
Right.
So, assuming that the rate of increase is directly proportional to the number of bacteria present, how do we express the number of bacteria present? N. But now we need what's called a proportionality constant. We'll use K. I think I used K. I did use K. Okay, so there's our original equation. Now what? Well, now I got to do some calculus. So I would like to separate the differentials a little bit here. So I would get dn is equal to kn dt. What's wrong with that? Hmm?
These derivatives.
Okay, so
Yeah, you have to get rid of them.
wrong derivatives on the wrong side.
Patrick?
You got the wrong derivatives on the wrong side.
Right, I got n's over here with the dt's. I got the dn over here all by its lonesome, so I'm going to move the n over here and get dn over n is equal to k dt. What can you tell me about k?
It's a constant.
It's a constant, and that's important to keep in mind. What's the next step in a separable differential equation? Take the integral. So we want the integral of 1 over n dn is equal to the integral of k dt. And notice what I did. K is a constant, so I moved k out in front. Some of you are getting in the habit of, when you look at an integral, if you got something you don't like or it confuses you, you just put it out in front. You can only do that with a constant. Okay, now the fun begins. What's the integral of 1 over n? Wait, question?
Is that du or dn?
That's an n.
1 over n dn.
1 over n dn, yeah. My n looks like a u.
Natural log of n plus c.
We'll put the plus c on the other side.
Got it.
kt plus c. Okay. Remember we talked about both sides would have a plus c, but our rule is normally when we're doing a differential equation, we attach it to the x. In this case, we're normally going to attach it to the time. Okay. Let's see. What next? I'd like to get n by itself. How do I solve for n?
Base e.
I'm sorry?
Unit base e.
Yeah, do the raised to the e trick. What's e raised to the natural log of n? N. And this is where it gets a little tricky. What's e to the kt plus c? Normally it's just e to the kt plus c, but we're going to split it up into two different parts. E to the kt times e to the c. Because we're going to end up solving for c. But going back to our discussion of c, what's c plus c? C. What's C times C? C minus C? E to the C. C, right. But I'm going to leave it in this form just for giggles. Okay. We stop at that point. And now we do a little bit of math. What are our initial conditions? Or what do we know?
T equals
T equal 2.
Let's talk about initial conditions. Jesse.
that n is number of bacteria present.
Good. And so initial conditions, at the initial conditions, what's T?
0.
Well, I answered it by writing it, sorry. And when T is equal to 0, what's N? 600, that's our starting amount. Okay. So the 0 goes in for T. Where's the 600 go? N. So 600 is equal to e to the k times 0 times e to the c. What about that guy?
It's 1.
It's 1. So therefore, what's e to the c?
600.
600. So e to the c is equal to 600. Which means we go back to this equation, and we now have, I got to get this out of the way, hold on. That's working well.
Do you solve for C now?
No, we don't care what C is, because again, C is e to the c, they're all the same thing. What we do care about now is that I still have the eraser on, and it doesn't write very well. We know that n, third time's a charm, n is equal to 600 e to the kt. Okay, so that's all the calculus. In pre-calc, you would realize that if you're looking at the PERT equation, again, remember the PERT equation is P naught e to the RT, you would know that your starting amount is 600, plug in for 600 and go. Question?
Would you solve for K?
Excellent. That's what we're doing next. Because we don't know what K is, right? Which is our rate. So we want to figure out how fast is the bacteria growing. So now we're done with the initial conditions because that gave us our starting amount. What do we do next?
Plug and shove.
What?
N would be 1800, T would be 2, and then you could, yeah. Just plug.
Then you could,
Solve for K.
thank you, solve for K. So 1800 is equal to 600 e to the 2k. First step,
Divide.
Divide by 600.
divide by 600. So 3 is equal to e to the 2k. Next step,
Log.
natural log of both sides. ln of 3 is equal to ln. That's a natural log, just it looks like an h, but what's the natural log of e to the 2k?
2K.
2k. So natural log of 3 is equal to 2k. So k is equal to the natural log of 3 divided by 2. Which is approximately, because that doesn't make a lot of sense, get out your calculators, tell me what the natural log of 2 is, and store that number, because we want the answer exact as possible. Will k be positive or negative? Positive, because it's a growth. There's more bacteria growing.
0.549.
Somebody confirm? 0.549. And again, store it. I don't want the 3 decimals. I want the entire number. Store it into X, store it into K, store it wherever you want. After all that work, we now know that our original equation would be n would be equal to 600 times e to the 0.549t. How do I use that to find the answer to B?
Plug in 440.
Plug in 4. Do it. confirmation, not that I don't trust you.
Yeah.
Yeah?
Yeah.
Is it exactly? It's not exactly 5,400, is it? Really? Huh. 5,400 what? Bacteria. If you have a bunch of them, that bacteria, if you have one of them, bacterium. Okay? Again, if this were pre-calc, you would start from this point and go on. In calculus, however, we're going to derive it. Now, does that mean you have to derive every homework on the every problem on the homework tonight? No, just 2 of them. But you still need to be able to do this process because you will be tested / quizzed on it / assessed on it at some point. And I'll do an example. In fact, I'll do the next example without deriving it. Okay, we good? Any questions on that setup? Beautiful. I'm erasing if that's okay. Yeah. Good. All right, what do we got next? Radium decays exponentially and has a half-life of 1,600 years. Who's taking AP Chem? What's a half-life? Have you done nuclear chem yet? You just did?
Yeah.
Well, how perfect is that? What's a half-life?
The time
Other than an outstanding video game.
the time it takes for
I get it.
half of something to decay.
Right. And where does that half go? It just goes away, right? So if I start with, what are we starting with here? I'm starting with 50 milligrams of radium, then 1,600 years later I have only 25 milligrams. So it's the time that it takes for half of it to disappear, hence the reason it's called a half-life. Will it ever completely disappear? No, because then another 1,600 years later, half of that half disappears, and you're all fairly smart in math and realize that it's never going to go away. Okay, so like in Chernobyl where they had a nuclear meltdown, there's always going to be, well, there's always radiation to start with, but it just lessens over time, it never disappears. Okay, find the formula for the amount of Y remaining from 50 grams of pure radium after 25 years. This one we're going to start right with the PERT equation. So I'm going to start with P equals P naught ERT. What do I know?
It's decaying.
Hmm?
It's decaying.
Good. I know it's decaying, so that R should be a negative number when we finally solve for it.
P naught,
What's P naught?
50.
Good. We know that P naught is 50. We know that R is going to be negative. Anything else? Yes, sir.
Why is it P naught?
That's just how it's,
Oh, I just didn't know.
right? You want to, yeah. You can call it P sub 0 if you'd like, but the cool kids call it P naught.
It's just awesome.
All right. Anything else? Okay, so we know that P is equal to 50 e to the RT. I've got too many variables there, so I have to start solving for variables. How am I going to solve for variables? What else do I know?
T,
I do know T. What's T?
1600.
And if T is 1600, if T is equal to 1600, then what's P?
25.
25. Good. That'll allow us to get rid of the T. That'll allow us to get rid of the P, which means we can solve directly for R. So 25 is equal to 50 times e to the 1600 R. First step, divide by 50. Hey, look what happens. Suppose I didn't know how much I started with. Could I still solve for R? Let's suppose I started with a ton of radium. How much would I have after 1,600 years? Half ton. So as soon as the first step dividing, notice that the starting amount is not relevant to solve for R. How do I solve for R, by the way? Natural log. So natural log of 1/2 is equal to 1,600 R. So R is equal to the natural log of 1/2 over 1,600, which is approximately, just to make sure that Grant was correct and we get a negative answer.
2 times 10 to the negative 4th.
Oh, it's a really tiny number.
Yeah.
Anybody get it in decimal form? Or did your calculator automatically put it in scientific notation? Negative 4.332 times 10 to the negative 4th. I could convert it if I want by moving decimal places over, but that works fine. And again, store that number so that you don't have to type it all in. Because when you start looking at a problem like this, there are so many decimal places way down the line that if you just stay with the AP standard of 3 decimal places, you're going to run into an inaccurate answer. Okay, so we know then that P, actually we should be using Y, but that's okay. It's 50e to the negative 4.332 times 10 to the negative 4th t. There's our general equation. In the last problem, our part B question involved time. How much would we have after 4 hours? This one, we're doing the other way around. How long will it take me to get 20 milligrams? So 20 is equal to 50e to the negative 4.32332 times 10 to the negative 4th t. By the way, will my answer be bigger or smaller than 1600?
Bigger,
Why?
because it took 1600 years to 25.
Good.
And so it would just take longer to get
Okay. How do I solve this?
Natural log. You divide by 50.
Then what? Natural log trick again. Okay, so that means that the natural log of 2/5 divided by negative 4.332 times 10 to the negative 4th will equal t. And therefore t is equal to
2,115.085.
2,115.085
That's 3 decimals.
years. Thank you. Yeah, I was looking for units there. That's a long time. When did the Chernobyl meltdown happen?
83, 84?
So, what is that, 30 years ago? A little more than 30 years ago. And just now they can finally go back into that area and at least look around.
Alright, here's what I know. There are many names for the number 0 in English and related concepts. The names of the number 0 include 0, cipher,
Never heard that one.
null, not,
Wait, Cypher was one of the
Not.
characters in Matrix, wasn't it? Wasn't that the guy that betrayed him in the Matrix?
Yep.
because he was the 1. Neo
was the one, but Cypher was a 0 because he just stabbed him in the back and killed everybody.
But then there's also love, duck, nil, zilch, zip.
Love in tennis, duck, but no not.
No, it's not. There's 2 nots. That's when you start talking about cipher and Neo. And
I missed. I talked over you. I apologize.
Yeah.
Okay. All right, we good? Next example. Newton's law of cooling. Any questions on this before I move on? Okay, the next one we're going to do from scratch because it's a little different setup. It doesn't fit exactly into the Purdy equation.
I'm just glad I wasn't the only one thinking that.
What?
Purdy. Purdy.
It sure is Purdy. Why are you using that equation? Because it's Purdy.
Duck would be the 0 for used by the batsman in cricket.
Oh,
I'll write that.
This is Wikipedia. It's going somewhere.
Yeah, you could invest if you'd like. According to Newton's law of cooling, the rate at which an object cools is directly... Speaking of cooling, where should you go if you're cold?
God.
Where should you go if you're cold? into the corner. You know why? Because it's 90 degrees.
Boo.
It's 90.
Mr. Reedy, I'm leaving.
Okay, see you, great. Thanks for coming. According to Newton's law of cooling, the rate at which an object cools is directly proportional to the difference in temperature between the object and the surrounding medium. If an object cools from 125 to okay. So we're going to start from scratch. So.
That's recorded too.
Oh yeah, I did record that. That's all right. So it's safe for prosperity's sake. Let me look at my variables here. I use y in this case. So dy dt. Y represents the temperature. Is directly proportional to the difference. So directly proportional means we have a proportionality constant. And what's a difference? Wasn't a trick question. What's difference mean? Subtraction. What are we subtracting? The difference in the temperature between the object and the surrounding medium. So the temperature of the object we defined as y. What's the temperature of the surrounding medium? 125, 100, or 75? 75. Because that's the room temperature. Okay, so there's our initial setup. Now we go through the process we did in the first one. I'm going to go a little faster this time, so stay with me. Separate the variables. dy is equal to k times y minus 75 dt. Get this over here. So 1 over y minus 75 dy is equal to k dt. Excuse me. Integral both sides. What's the integral of y minus 75? 1 over y minus 75.
Natural log of y minus 75.
Correct.
Shouldn't K be on the outside?
It can be, it doesn't matter. Okay. Now let me give you a little caveat here. A lot of you are taking any function that's underneath a 1, and when you take the integral, you're just naturally making it a natural log, no pun intended there. But you have to be careful. Sometimes this function you have to do as a UDU. This one actually should be done as a UDU, but if you do it as a UDU, what's u? Y minus 75. So what would du be? 1, and it doesn't matter. Okay. But don't automatically just take it to be the natural log. This one happens to work out that way. Natural log of y minus 75 is equal to the right side, kt plus c. Do our e trick. So y minus 75 is equal to e to the kt times e to the c. I skipped a couple steps in there because you're all fairly bright, and hopefully you can follow me. Yes? Okay, because e to the kt plus c is e to the kt times e to the c. All right, what do we know?
T equals 0, y equals 125.
When t equals 0, y equals,
125.
well done, degrees.
T equals 1/2.
Hold on one second. 125 minus 75 is equal to, what's this? 1 times e to the c. So e to the c is equal to 50. Okay so far? We're good? Which means that y minus 75 is equal to 50 times e to the kt. Will k be positive or negative?
Negative.
Are you asking or telling?
Telling.
Telling?
Yeah.
Why?
Because it's losing heat.
Good enough. What do I do next? So this was our initial conditions. What other chunk of information do we know?
At a power 1 times
T equals
1/2.
1/2. Y equals Hondo. How did you know to use a half instead of 30?
This is an hour.
Could I use 30?
Yeah. Because when you did 0 as hours before, it wouldn't affect it if it was hours for minutes or.
So when I solve this, I'm going to get a rate, correct? If I solve this using 30, would the rate be the same?
In terms of
No.
units, yes. Does that make sense?
Meaning,
Oh.
It wouldn't be the same number, it's
Right.
it wouldn't be the same number,
just,
but
it'd be the same rate.
You have to define.
Yeah.
Because there's units.
good, you have to define units. That's the only point I'm trying to make, is that if you, in this particular case, if you want to stay with hours, great. You're going to value for the rate. That rate will be different than if you do minutes. It doesn't matter as long as you stay consistent with the units throughout the entire problem. Okay, so that means this becomes 100 minus 75 equals 50 e to the 0.5 k. All right, solve for k. Don't forget to store. Is it negative like you thought?
Yep.
Okay. Is it a reasonable number or is it ugly like the other one?
It's reasonable.
What do you got?
Negative 1.386. And that's obviously rounded.
Y minus 75 is equal to e to the negative 1.386, whoops, 6 t. And we're going to put a box around that because there's our, pretty much our final equation that we're going to use that, Claudia?
Would you multiply that by 50?
Oh, thank you. I forgot my 50, forgot my initial units, thank you. The last problem, or the last question then in the problem says find the temperature at the end of the next half hour. What's T? 1, correct. So we want to know at the end of the hour. Plug and chug, get an answer. What's the temperature after an hour?
87.
You got it? 87.5 degrees. Whoops, 87.5 degrees. So this process that we went through from here down to here is what's called deriving a growth or a decay problem. On tonight's homework, you will derive problems 11 and 12. Now I think there might have been some confusion. Hold on, let me stop the recording. Any questions on this? Can I erase? Here, I'll just do that.
Then you have all those.